Before I delve into any stealth platforms on this channel, I thought it would be prudent to give viewers who may not be familiar with stealth a brief introduction to it. Stealth technology, also known as low observable technology, is defined as the reduction of various signatures including visual, infrared, audio, radio frequency, and most notably radar cross-section. Stealth utilizes various technologies to achieve these goals including, but not limited to, materials and shaping. In the 1960s, Soviet physicist and mathematician Petr Ufimtsev, working at the Central Research Radio Engineering Institute of the Defense Ministry of USSR in Moscow, began developing equations for predicting the reflection of electromagnetic waves from simple two-dimensional and three-dimensional objects. He gained permission to publish his research results internationally because they were considered to be of no significant military or economic value. How wrong this would turn out to be. Dennis Overholzer, a stealth engineer at Lockheed, had read the publication and realized that Ufimtsev had created the mathematical theory and tools to do finite analysis of radar reflection. This discovery inspired and had a role in the design of the first true stealth aircraft, the Lockheed F-117 Nighthawk, better known as the StealthFighter. Northrop also used Ufimtsev's work to program supercomputers to predict the radar reflection of the B-2 Spirit, better known as the StealthBomber. When we think of stealth, we think first and foremost about the reduction of the radar cross-section of a platform. The goal of reducing a platform's radar cross-section is to minimize the size of the radar return of the platform back to the interrogating radar. There are many factors that can contribute to an aircraft's radar cross-section. Large reflective surfaces such as square surfaces that meet at 90-degree angles, vertical tail fins, disjointed edges, protruding elements such as sensors, untreated cockpit canopies, exposed engine blades, and externally carried weapons and fuel tanks can all contribute to a large radar cross-section. First-generation stealth reduced the radar cross-section of aircraft primarily by shaping, as typified by the Lockheed F-117 Nighthawk stealth fighter seen here. Lockheed used faceted surfaces to deflect radar waves away from the interrogating radar. They also reduced the number of angles used in the wings and tail fins, and matched their angles. Lockheed used engine intake cover grills with holes smaller than the wavelength of the radar it was defending against in order to mask the aircraft's engine blades. In addition, Lockheed used sawtooth patterns to break up straight lines around surfaces, such as landing gear doors, cockpit windows, sensor bays, refueling receptacles and access panels. Weapons were designed to be carried in an internal weapons bay, and the entire surface of the aircraft was covered in radar-absorbent material. Second-generation stealth, as typified by the Northrop Grumman B-2 Spirit stealth bomber, used more advanced shaping techniques using compound curves that were made possible by supercomputers which were not available when Lockheed was designing the F-117 Nighthawk. In addition to using compound curves instead of faceted surfaces in its airframe, the B-2 utilized the flying wing planform, which it had first developed during World War II for the XB-35 bomber. The flying wing planform helped to greatly reduce the B-2's radar cross-section. This planform also enabled the aircraft's engines to be deeply buried in the wing. They were fed by serpentine-shaped engine intakes which not only hid the engine's fan blades, but also helped reduce the aircraft's infrared signature by enabling cool bypass air to mix with the hot engine exhaust before exiting the engine nozzles into external troughs that enabled the further mixing of cool air with the hot engine exhaust in order to further reduce its infrared signature from ground-based infrared sensors. Northrop Grumman also used sawtooth patterns on the engine inlets, engine nozzles, landing gear doors, weapons bay doors, and the entire trailing edge of the aircraft in order to further reduce its radar cross-section. The B-2's radar cross-section is further reduced by utilizing a large-capacity internal weapons bay and covering the entire aircraft in radar-absorbent material. Foreign competitors to the United States have scrambled to try and catch up with the United States' decades-long lead in stealth technology. Over the last 20 years, other nations have begun to develop and field their own stealth platforms. China introduced its first stealth aircraft in 2017, the Chengdu J-20 Mighty Dragon, a fifth-generation air superiority fighter. Russia introduced its first stealth aircraft in 2020, the Sukhoi Su-57 Felon, a fifth-generation air superiority fighter. In addition, other foreign nations are beginning to develop sixth-generation fighters designed with stealth technology planned for introduction in the 2020s and 2030s. These sixth-generation fighters include the British Aerospace Tempest, to be produced in conjunction with the United Kingdom, Italy and Sweden. The Dassault Airbus FCAS, to be produced in conjunction with France, Germany and Spain. The Mitsubishi FX Godzilla, to be produced for Japan, and the Korean Aerospace Industries KF-21 Boramae, to be produced for South Korea and Indonesia. Stealth will continue to play an integral part of all future weapons platforms for the foreseeable future. I look forward to sharing many of these stealth platforms with you in future videos. I will endeavor to upload a new video each week, so make sure you subscribe and hit that notification bell to know when I have uploaded a new video. I hope you will enjoy this content and continue to come back for more.